Hello, and welcome to my radio frequency communications lecture, my introduction presentation that I held live. This is the recording of it, and this is actually a voiceover right now because I had some technical difficulties, but bear with me. It will get to the live audio in just a little bit. So, to get things started, what is RF communications? It involves the use of radio waves to transmit information, like data, voice, video, across distances without any need for physical contact. It does this through electrical magnetic waves, or electromagnetic waves, and these are radio waves that travel at the speed of light. Now, typically, we talk about these in terms of frequency, and the frequency range is from 3 kilohertz to 300 gigahertz. That's the typical range. It can vary vastly. And it's measured in cycles per second or hertz. So let's get into frequency. The frequency is the number of waves for a set period of time. So you have to have a period of time here to actually measure your frequency. Now, like I said, it's measured in hertz, Hz, and 1 hertz is 1 cycle per second. Now, you'll commonly see them in multiples of 1,000, a million, or a billion, and these are your kilohertz, megahertz, and gigahertz frequencies. So with sub-gigahertz frequency, the thing we're going to be focusing on in this video, it's mainly going to refer to anything that's under a gigahertz range. So most of our stuff is going to be in the megahertz. If you're talking about like low frequency RFID, for example, that would be in the kilohertz, particularly 125 kilohertz. Now your NFC is going to be using megahertz, around 13.56 megahertz, and we'll get into what the different kind of ranges are for specific uses in a little bit, but just so that you're aware, frequency is measuring the distance between your waves here. So, amplitude's next. Amplitude is the height of the wave, and it usually represents the strength or intensity of the signal. It's used to carry information via modulation, and it's used as AM.
It should be fast.
We're going to get back to the official audio now of the live recording. Thank you. Okay. As long as you can still hear me, then I'm done. I'll be putting the recording on YouTube. So for everybody that is watching on YouTube, I'm sorry you could not hear me for like a good portion of that. I was just going over the agenda and the legal disclaimer, which I highly recommend you read. All right, let's get back into it. So amplitude, this is going to be your height of the wave. It will represent the strength or intensity of that signal. So the higher the wave, the stronger the signal. And it's used to carry information via a certain type of modulation. And we call it amplitude modulation because we are modulating the amplitude. And this will go by AM. That's how it's abbreviated frequently, not frequency. Moving forward. So how do we get this data into the air? Through modulation. So we have a picture here with showing 3 different waves. The first wave is our message signal. Now this message signal is an analog, not digital, but you just look at the peaks here. So this peak is going to be a 1 in binary. This valley is going to be a 0. And one more thing to note about amplitude is it only refers to this top portion. If you're looking at the entire thing here, that's actually 2 times your amplitude, just to keep in mind because that's something really easy to mix up. So looking at our values here, we have 1 0 1 0. So how do we get that message onto a RF wave? Well, we need to transpose it with a carrier signal. Now a carrier signal is just a sine wave that we are going to modify in different modulation methods to actually get it into a form that works. So you can see with this GIF here, we have your signal, and for amplitude modulation, the amplitude, so the height of the waves, is actually changing with the 1s and 0s, But for FM, frequency modulation, it's just the frequency that's changing. So as you saw in the previous slides, the frequency is higher when they're closer together. And now you can see that it's closer together where the amplitude is higher, where we have our ones. So, yeah, is stuff blurry to you guys? That's not good. Let me change some things. Does this look any better? Okay, perfect. I'm sorry about that. Were you guys able to actually read the data, the graphs and the text and whatnot? Or should I go back? Okay. Cool. So, the waves get smaller here. Not smaller, closer together here in FM to represent a higher frequency. And that's changing the frequency, modulating the frequency to represent different parts of data. So we're going to have a quick comparison here, AM versus FM. Amplitude modulation encodes data by adjusting just the amplitude of the wave. Now, AM signals can travel further than FM signals, especially at night because they actually can bounce off the ionosphere. And that's a big part of AM transmission, is finding the right frequency and the right way to modulate it, that it actually can bounce and travel further than it would otherwise. Otherwise, it would just go out into the sky. Higher frequencies will pierce through it and not travel. So FM normally requires a line of sight, whereas AM does not. But it is more prone to interference, but it also requires less power. Now, for frequency modulation, we are encoding the data by adjusting the frequency of the wave. So it has shorter range, but it does provide a higher fidelity and quality, and it's also more resistant to interference. So you're going to want FM on stuff that actually requires high quality, like audio and video. AM modulation. So we're going to go into the modulation techniques here. The first one is called on-off keying. This one is probably the simplest, and it's also very, very common in sub-gigahertz communications. So the signal is either there or it isn't there. If a signal is present, that will represent a binary 1, and if a signal is not present, it will represent a binary 0. So the signal is just the carrier wave alone. Frequency and amplitude aren't really changing in this, typically. So you guys can all see the chart here. We have one period of time that we are broadcasting, and then a period of time that we're not. Now the other one is called amplitude shift keying, and you've probably seen this before and wondered why, when you're trying to scan an RFID tag, it's asking you something. That is what this is referring to. It's not referring to asking, it's referring to amplitude shift keying. So there's a continuous signal, but the amplitude either shifts up or down. A shift up is going to represent R1, and a shift down is going to represent A0. Now this uses slightly higher power because we are always transmitting. The carrier wave here is always going to be there because it's not off, it's just at a lower amplitude. Now we'll talk about FM modulation, but we're not going to go deep into FM modulation because most of your sub-gigahertz devices that you're going to be trying to communicate with your flipper are going to use amplitude modulation. But I am still going to cover it because this is an intro to RF and not just the FlipperZero. So frequency shift keying is an FM modulation technique where we basically just shrivel up our frequencies. We make them higher when there's a 1, and we stretch them out, make them lower when there's a 0. Now, it's also referred to as 2FSK, and that just means that there's 2 frequencies that are encoded. This is traditional. It doesn't mean anything extra, but there are variations of this that use like 4FSK or more, and that is how you get more data through a single wave. But we're mainly going to be dealing with 2FSK, and I believe the FlipperZero can only do 2FSK. I could be wrong there though. Now, phase shift keying is another way to modulate signals, and this is the other part to the IFRD scanning. So when you, I think I could pull it up. I'll do that later. This is a little more technical than the other versions of modulation, and it's a little harder to actually see what's going on here, but it uses the phases of the wave to actually encode the data. And it's a similar thing you'll see here, BPSK, and that's because it stands for binary. There's only 2 steps or 2 states that your signal can be in. GFSK, is that a Gaussian frequency? Cool. Yeah, I'm not going to go into that, but that is good to know. So if you're not understanding what exactly is going on here, so on our 1 bits, we have a rising phase, and then it'll be flipped or reversed on our 0 bits. Now we'll get into the actual stuff on the flipper here. So when you go into your sub-gigahertz app and then go to read and then go to config, you will see a bunch of things. One of which is your frequency. That one's pretty self-explanatory. But then you have your modulation here. So to break it down, you have your type of modulation, AM or FM. There's also some other modulation types that aren't available in the official firmware, but you'll mainly be dealing with these for now. So the number here is the bandwidth that it's going to apply a filter to, and it's in kilohertz. Now the larger bandwidth is going to pull in more, and this is super useful when you're trying to detect a signal that is hard to find. But once you can get that signal dialed in, going for this lower bandwidth will actually provide you a cleaner signal because it'll have less interference and less noise. But if you need more range, then 650 will be where you're at, and I would say that'll be most of your searching at first. So some other essential terminology here. We have gain, which is the power or amplitude of a signal, and it's measured in decibels. dB, it's not measured in decibels, dBm, decibels per, I don't actually know what dBm stands for that, but it stands for 0 dBm is 1 megawatt, not milliwatt, I mean, of power, and it scales. Now that is that's a set number. That's always true. Your gain will vary depending on a lot of different factors, and it's not like a universal number. RSSI, you'll be using this a ton. This is your received signal strength indicator, and it's a measure of the strength that the receiver can pick up. Now, this will be used for kind of seeing the proximity of the signal, and it can also show you quality. Quality is not really the right word to use here, but it'll let you know how strong a signal is. Noise is the unwanted part. So this is anything that's going to interfere. This can be caused by other devices, but it can also be caused by the surroundings. And this is normally measured as signal to noise ratio, and this is used a ton when it comes to radar. So the steps to sniff an unknown signal. First thing you're going to do is open up your frequency analyzer and set the RSSI threshold. Now, if you're using the flipper without any external modules, then you're going to want to set the RSSI threshold fairly low. This is because the receive range is not very strong on the base flipper, and so if you set it too high, you're not going to be able to detect anything. Now, once you have it set, you click the button on your remote and trigger the sub-gigahertz signal, and look at the screen. The screen will tell you what frequency it picks up, and it's quite cool how it does this. It's actually using a variation of frequency hopping, just a very, very, very fast frequency hop, where all it's looking for is the frequency coming in, and if there's a signal or not. Once you have that frequency, then just open up the sub-gigahertz read and adjust to that frequency. Then you want to wait to see if the signal gets demodulated or not. And if it's not, you can change your modulation settings and kind of just play around with it. Now, if the signal isn't using a known protocol, then it will not show up. You can check on the FlipperZero website which protocols they have implemented, and custom firmware usually has several additional protocols that are entered. Can you hear me now, or am I still being cut out? Cool. Did you miss anything? Awesome. If it's not a known protocol, then you're going to have to use raw. I recommend you try both your AM settings and FM settings. Don't be afraid to revisit the frequency analyzer if things aren't coming up right away. Again, this is only for the protocols, so I don't appreciate that comment, Yapper, because I'm not even living in a dorm. This is my own. Okay. Anyways, a live demonstration. So I had everything set up through OBS, and that's probably why it was all wonky. But I just need to switch out the screen I'm sharing from real quick. Change window to QFlipper. Okay, so can you still hear me? I'm going to constantly check. Cool. All right, so you are going to go into your sub-gigahertz app, and then you're going to go down to your frequency analyzer, and I have mine set all the way up for the threshold because I was using an external module, but I'm going to bring it down. Now, if it's all the way at the bottom, you'll get ghost signals like this that are being broadcast from who knows what, so you don't want it exactly all the way down, and it's depending on what you're trying to get. If you're really close to the remote, then you might actually want to set it higher. This is something that just requires a lot of experimentation. So now that we are in the frequency analyzer, we can wait until we get a signal. So I hope you guys are ready to wait for a while, because if you think I planned signals, then I don't know. I'm just joking. So I have a signal come up for 314.98 megahertz. Now on custom firmwares, you can directly go from this into the read section, but on original firmware, you're going to have to just remember this. I'm going to now click on that, and it's going to start a fixed scan. Now you can see my modulation is set to AM650, again, larger range. Now we're going to wait for this mysterious signal to come again. Oh, would you look at that? Okay, so this is a known protocol because it showed up here. If you click on it, then you can see more about the protocol. You can see the, usually it'll show you everything about the key and stuff. Depending on your protocol, it will vary very differently. Now on original firmware, you are limited in what you can save. I'll go into that later. Yeah, this is this is a remote that I programmed to work with my Arduino to turn my light on and off. You are welcome to steal this. Now, let's say that someone is spamming a remote. You can see the actual signal strength with the bar on the bottom. So there's your live demonstration of read. All right, let's get back to the PowerPoint. Okay, so static versus dynamic codes. Static codes are also known as fixed codes, and these are unchanging codes that are transmitted each time an action is performed. An action being sending out the signal. So this is far, far less secure. Guys, okay, people are going to be confused watching the recording. They're talking about driving by my house and making my lights flicker. Anyways, static codes, this is a static code. That is why that's possible. Less secure because it can be easily cloned. Their common uses are for garage door openers, really the older models. You'll see one protocol, Security Plus 1.0. That is a static code. But most simple remote controls are also using static codes because security doesn't matter nearly as much. Now for dynamic codes, yeah, that's a good idea. I will do that. So everyone watching, you should not be watching. Everyone watching at home after the fact. Dynamic codes are hopping codes, so they are going to change following a specific algorithm. These usually use a seed to generate the whole key section, and then that same seed will be on the receiver, and that is how they determine which one is which. They're more secure and highly resistant to replay attacks, as a captured code is only valid for the current use and will not work again. This is your modern vehicle key fob, or your new garage door openers. And this is why you can't just scan your car keys, because it will not work. The button that you pressed will have already been used, and so that recording that you got, which you would probably have to record using the record raw, which I'll get into, just won't work. Oh, and if you do get it to work through a replay attack, pay attention to may require a remote resync. You can desync your little key fob, and that's not fun. I haven't done it, of course. So now I gotta switch back to QFlipper, and I will show you how to use read raw. Cool. Yeah, car dealerships do charge you for those, I've seen. Now I haven't desunk a remote on my own, but it is very easy to do. So read raw is just located here under read, and I don't know if it's a feature for official firmware, but you can set an RSSI bound, and you should absolutely do this, because what read raw is doing is it is recording everything. It's recording everything that's coming in, and so all the noise that's also going around is also being collected, and you do not want that if you're trying to replay that. And I'm not sure exactly where you set it. Oh, you probably set it in config. So I have mine set to -60. You can detect the remote, see where it's at, and then set it higher or lower depending on whatever. So I am going to, actually, just for the sake of it, we're going to do a different remote. So I'm going to open the frequency analyzer back up. And let's do this one. So this one is on the higher frequency range. And you'll tell just the frequency between your like 433 megahertz transceivers, and between that and the 800 megahertz stuff, the range difference is dramatic. And that just kind of proves the whole frequency difference between FM and AM. So now that we have our frequency, I'm going to click and hold to open it on fixed scan. Oh, I was going to show you read raw, my bad. So you're going to want to click the record button, make sure it's set to the right frequency here, and it's going to start recording. Now, it is stopping, and I guess that's because there's no frequency that's over the threshold. I wonder if that's a new thing. Anyways, when the remote signal comes in, you will see a blip of activity. And you definitely don't want to capture this much data. Sorry for anyone's eardrums that just broke there. What you're going to want to do is time it so that you just record one clean signal. Now this might actually be a little too high of a threshold here. There we go. So now I have the signal button pressed saved twice. And so I can either directly send it, or I can save it and try to demodulate it. And I actually should just press it once. And we're going to save this as raw. Now we have the option to decode it. And would you look at that? So if the signal that you captured from raw is a signal that the protocol is actually present for, then you can actually decode your raw signals. Most people don't know what this does, mostly because when you run it on a raw signal that isn't a protocol, then it won't do anything. But as you can see here, we found this remote. This also is a rolling code remote, I believe. It is. And even this is not rolling the codes. Now, if we were to also find it in this section, same remote. So you can see that read raw does work. And maybe it's a good thing that the rolling codes aren't working. Yeah, alright, moving on. And I apologize for the frequent switching. Just gotta make do. Now we're gonna explore RF with some more advanced techniques. The first one is going to be frequency hopping. So frequency hopping allows you to scan a wide range of frequencies to discover signals that may be on different frequencies. An example of this is if you know a specific remote can use multiple frequencies for transmission, then you can set those frequencies and then turn on hopping so it'll rapidly swap between them. And then if it starts to pick up that signal, it'll actually stop hopping and start recording. So this is the premise behind your frequency analyzer and the spectrum analyzer app, as it just goes really, really fast and doesn't stop. But here it is stopping, and you can enable this in the config menu as I showed you. And you can also add your own frequencies. Now, I know in custom firmwares you can do this through the UI, but you can also do this through editing the settings file in an official firmware. I'm not sure if they updated to include that feature or not. But that's how you would add your own frequencies, which is something you would want to do if you're looking for a particular thing. And I will now display this. There we go. So we're going to go to read, and actually, yeah, we'll go to read, and we're going to turn on hopping, and this is going to make the frequency just blank, not show, and it's going to go with the default frequencies, and there's a handful of them. These can be toggled on or off. In custom firmware, I know you can do it through the UI. I'm not sure for official firmware. Once it's enabled, same thing with choosing your modulation. You'll see that when you read, it is going to rapidly go, and where it picks up a little bit of signal, it kind of pauses for a second and tries to read what's actually going on here. And so I'm going to play that same remote. Actually, that remote's not in these frequencies. Let me use a different remote here. I'll use one that is a maybe I shouldn't use this for demonstration. So there's a remote. Oh, there we go. Security Plus 1.0. So we can open it up here, and now we have someone's garage. So that's just an example of how you would use frequency hopping to collect something that you don't know. I would do some research on the FCC website about a particular remote or device, and then once you find those frequencies, program them in, go to hopping, and see if you can grab them. Now, most of the time, not even most of the time, a good amount of the time you will need to actually record raw and just use the raw file. Decoding it won't work. And again, that's for anything without a known protocol, so your car keys basically. And that is why you also don't do your car keys. It's not good. Now let's go beyond and below sub-gigahertz. So we have our main frequency bands here. There's actually a ton of frequency bands. This is just covering the main three. We have low frequency, which is very long wavelengths that diffract around obstacles, and not low frequency, but I think very low or ultra low frequency. Oh, am I still in Q Flipper? Whoops. Yeah, I'm definitely going to do a video afterwards. There we go. Alright, so like I was saying, low frequencies travel further, and they're good for when you don't need a high data rate. High frequency bands, they still reflect, but they don't reflect as well. Now, I believe sub-gigahertz is still within the high frequency band, not in the low frequency band. High frequency is going to be for your satellites and a lot of other things. Ultra high frequency is what you're going to need if you want some quality TV, anything that needs high data rates. So let's talk a little bit about some other things that are not sub-gigahertz. We're going to talk about Wi-Fi here. So Wi-Fi operates in two main frequency bands. We have 2.4 gigahertz and 5 gigahertz, and you've probably seen in your home network that both are being broadcast. Now, in your router settings, you can enable or disable one or both, I guess. And this is really up to if you need it or not. If you don't need it, it's probably a good thing to disable it because it is vulnerable to a lot of different things. But it provides wider coverage and better penetration through objects, through walls, and whatnot. And so this will be perfect for your IoT devices. I think I put that here, yeah. But your 5 gigahertz network, this will be your faster network, so this is what you want for most of your things that need high bandwidth. Wi-Fi uses a variety of modulation techniques, but they're all kind of built off of the ones we talked about, just kind of varied versions. So BPSK is our binary or bi-phase shift keying. We have our QPSK, so this is our quadrature phase shift keying. And then we have some weird ones, 16, 64, and for 5 gigahertz, 256 quadrature amplitude modulations. So these are a little more advanced than the ones we just talked about, and that is because they allow for more bits to be encoded per wavelength. And how does that work? Well, it increases kind of the amount of little things that can be detected as different bits. For example, for QAM 256, there are 256 possible states that it can be within a wavelength, which is crazy given we started at just 2. Wi-Fi uses channels to help reduce interference, and there's 3 non-overlapping channels that you'll see. Channels 1, 6, and 11. You can mainly configure most of this stuff inside your router settings. Now, I wouldn't go changing stuff if you don't know what you're doing, because people screw up big time doing that. And I also wouldn't overlap your your channels. You'll be kind of defeating the whole purpose of it. And each channel has a 20 megahertz bandwidth, with the exception of 5 gigahertz networks, which can actually use 20, 40, or 80 megahertz channel bandwidths. For 2.4 gigahertz networks, you have a data rate of up to 600 megabits per second, and for 5G, you can get up to several gigabits per second. This is it's not really a marketing trick, but when you see internet providers advertising for their internet plans, I think they make it seem like megabits per second is megabytes per second because we're used to dealing with everything in megabytes, and we're really not used to megabits. And so a lot of people confuse megabits per second with megabytes per second, and I've seen that so much when people talk about their internet speed, but now you know. So again, the 2.4G network band will be used mainly for your IoT devices because of this longer range. Now, I don't think that's the primary reason. It's probably because the chipset is cheaper, and they are vulnerable to attacks. So a lot of them can be taken down with deauthentication attacks, and that's management frame stuff. Handshake collection can be used to grab the handshake, and I think it'll be too much to go into the 4-step or 4-part handshake for Wi-Fi. that's a whole topic on its own. Wi-Fi password cracking can then be used with those handshakes through finding the hash. Once you find the hash from the handshake, then you can use a hash table online or download a hash table and use Hashcat to actually get the Wi-Fi password. So 2.4G network is not very secure, and you can only go up to WPA2 standards. You cannot get WPA3 on your 2.4 gigahertz band, and that's why I say if you're not using it, just don't enable it. It's not needed. Also, have you ever had your Wi-Fi stop working when your microwave is on? If so, that is because the microwave is basically working as a 2.4 gigahertz Wi-Fi jammer, just because of the amount of EMF it produces. And you can actually test this when you go to your microwave if you want to get on your Wi-Fi and see the difference. Thank you, carbonated yapper. Let's talk about Bluetooth a little bit. So there's two main versions of Bluetooth, Classic and Bluetooth Low Energy, and they both use the 2.4 gigahertz network band, but they're quite different in how they work, very, very different in how they work. Regular Bluetooth is a technology used for exchanging data over short distances, and Bluetooth Low Energy is mainly used for short burst power saving purposes like AirTags, and the Flipper actually can only do Bluetooth Low Energy, and a lot of devices these days are actually Bluetooth Low Energy, even though it wasn't initially designed that way, which is quite cool to see all these different functionalities. Both versions use Gaussian frequency shift keying, and as mentioned earlier by Code All Night, the Flipper can also do this. And Bluetooth Classic can also use different variations of phase shift keying. I think there's 3 different types that it uses. Bluetooth Classic also has channels, and it divides it into 79 channels, while Bluetooth Low Energy only divides it into 40. And I already kind of went over this here, but it's slowly replacing Bluetooth Classic as time goes on, and eventually we won't see much of anything with Bluetooth Classic, for better or worse, because BLE is a very dense topic. I have looked into it. I have worked with it. It's not very fun. RF security. So let's go over the security aspects of Bluetooth and Wi-Fi. This is very, very brief because these topics are huge. And yes, Willie, it is so much fun. Just not coding it. For Bluetooth security, we have frequency hopping spread spectrum. So this is really, really cool. And it's where we hop between 79 channels to reduce interference. That's not the main purpose. It's mainly for enhancing security here, so that one channel can't just be spied on. And it has 1,600 hops per second, which just sounds cool to me. We also have, I guess it's the same thing, kind of told. Each Bluetooth packet switches frequencies as well, every 625 microseconds, and so it's very hard to actually hack into Bluetooth. As for Wi-Fi, we have 2 main standards that are used now, WPA2 and WPA3. WPA2 introduced AES and some MAC protections, MAC being message authentication codes, not being like the MAC of your device. They are different things. WPA3 greatly increases the security of everything. Now, we also have SSID hiding, and that is a major thing that any IT person should be aware of when setting up internet for their company. Normally, you're going to want to hide your SSID, and there's no reason to have it public in that sort of environment where you're going to become a bigger target for hacking. We also have some other things like MAC address filtering, firewalls, and guest networks is something you can actually utilize at your own house. And I highly, highly recommend guest networks. So create a guest network. Most routers these days can do it. And your guest network is going to be like your network you give to friends, non-close friends, or those IoT devices that have terrible security because that's not what their focus is. So put your IoT devices on a guest network. Why this is special is because it is actually completely segregated from your main Wi-Fi. And so they're not going to be able to get to your main Wi-Fi like they would on a 2.4 gigahertz network that's running along with your 5 gigahertz network. Now we're going to talk about something a little controversial. But we're just going to talk about it from a cybersecurity standpoint. So I am a cybersecurity engineer, and I had a lot of training and research and study on jamming, specifically when it comes to UAVs and radar. So I'm going to give you kind of a high-level explanation of this stuff, but the actual stuff that matters. So here are your types of jammers. You have your constant jammer, which emits continuous radio noise, and this disrupts communications regardless of the channel activity. We have a deceptive jammer, which sends continuous packets, and this overwhelms the network and prevents other devices from transmitting. Think of it like a DOS attack. Don't think of it, it is a DOS attack. Random jammer. This will alternate between active jamming and idle states, which conserves energy, and what I think is the main appeal for this is that it complicates detection efforts because it's hard to pinpoint where it's at or what's happening. And then you have a reactive jammer, which activates only upon detecting transmission, and this makes it highly effective and difficult to detect due to its selective nature. But fortunately, we have some countermeasures as well as ways to pick apart when a device is being jammed. So signal monitoring is a basic approach, but it is effective. Devices will monitor the signal strength and energy to detect deviations from normal conditions, and this can suggest potential jamming. You can also get false positives here, depending on how much energy is coming at you that you're actually needing. Like a RAID, for example, if that was in RF terms. We have statistical analysis, which employs methods like signal strength spectral discrimination to differentiate between the usual signal fluctuations that are going on with your legit RF and jamming attempts. Then you have carrier sensing time, and this is time measured in the 802.11 protocols to spot jamming, as jammers typically increase this metric, and it's very easy to pick out. Packet delivery ratio, PDR, you can monitor packets and distinguish between network congestion and jamming, with lower PDRs hinting at jamming activities. So this is how much of your information is actually making it through. And I'm going over all these detection ways because it's very, very easy for the government and other agencies to know if someone is jamming. Very, very easy. And they will come after you if you are doing it, especially if you're doing it in places where there's a lot of people. So please don't do this. This is highly illegal. I just want to teach the aspects behind it, the science behind it, as I think it is important for us to understand this to be able to better secure ourselves. And you can see with all of these new detection methods that this works. So we also have spread spectrum techniques like direct sequence and frequency hopping, spread spectrum, and they also mitigate the effects of jamming. So we kind of talked about spread spectrum for security of Bluetooth, but that alone can help with jamming, depending on how the jamming's done with relation to frequencies. So now it is Q&A time. If anyone has questions, please drop it in the chat. And I will say this again, I will re-record this video, and I might even add a little bit of information on things that I might not have touched on quite as well. Also, if you guys have any suggestions, you could drop them in the chat. You're welcome. Hopefully you learned something. I wanted to cover both the basics of using the Flipper's sub-gigahertz features, as well as how it works on a lower level, on a signal level. If there's no other questions, then thank you very much for watching, and that concludes the presentation. And the recording will be on my YouTube channel, so I will drop a link to that once it's uploaded, and it'll be pinned somewhere, or an announcement will be made. Yeah, it's just YouTube at Matthew Kucinich. I hope that's the right channel. Let me see. Okay. Yeah, you're welcome. If you have any questions after the presentation, please feel free to just ping me. And if you have any questions about JavaScript exfil, there's this guy I know that actually wrote a major JavaScript exfil script, and he's a real one, and he would love if you pinged him. Alright, see you guys in the next presentation, maybe I'll do a car hacking one. Thank you for bearing with me for all of the issues happening. I've never used the streaming function for Discord before, and now I know not to stream using OBS. Yes, I definitely want to do a talk on CAN. I've given several presentations now, in-person presentations on car hacking and car security, all through the CAN bus. And I actually already have the slides because of that. And a pre-recorded demonstration would be cool. Do you guys want to accelerate your car with your FlipperZero? Because you could do that. Just don't. And wait for the CAN Commander board to be dropped very soon. Wait, was that announced yet? Whoops.